So it is my great pleasure to have here Stefan Wuttke from Basque Center for Materials Applications and Nanoscience. Stefan is a huge friend of Ukraine, and he supports us in many ways, and started several projects and on supporting Ukrainian chemists. And as a part of this initiative, he agreed to give several lectures on material science, in which he is a huge specialist, in which is he has huge experience. So Stefan, a few words about Stefan. He received his PhD in Berlin, and then moved to Spain, where he has his independent research group, which mostly focuses on material sciences, as I have mentioned, including, for example, nanoscience, metal organic frameworks, and other aspects. And we shall have 3 lectures on material science, which is for students of first year of master degree and the fourth year of bachelor degree. So Stefan, you have your time, please.
Thank you so much. Do you see the main slide?
Yes.
Yeah, it's perfect. So yeah, thank you so much for the invitation and introduction. Yes, I'm quite excited to be here and to give a lecture about material science today, about advanced characterization techniques. I will tell you later why I choose this in the beginning, because you have to know I'm at the institute. And I'm not teaching anymore, so it's even big pleasure to teach and to try to inspire you with certain things of thinking in material area. But before we start about this, I would like to advertise a school that we are organizing, a European chemistry school for Ukrainian researchers. So we are just doing it, and then I think in 1-2 weeks the web page will be finished. So it will be people. We have already 2 Nobel Prize winners that give a lecture. They will speak about chemistry, but also about the institution. And the idea of this chemistry school, that you see what is happening in Europe now up to date. They will try to inspire you with new ideas, and also just maybe giving you the possibilities to make networking or even later collaboration. But I will tell you next week or in 2 weeks, when the webpage is on, the details about this. Then short to me, where I am. So you see, wait 1 second, I will make here the laser pointer. So here's Kiev and here's Bilbao. I have the pleasure to be close to the beach. So 200 meters from my flat is the beach, and Bilbao is a quite nice place to live and also to make research. At first about the place, if you are loving Game of Thrones, also this is the picture here from Game of Thrones, it's actually here, it's 10 kilometers from here. So the castle and the way up, you know, when the dragons was flying, this is here in Basque country, so very important place to visit. And here the Guggenheim is quite known. So we have a nice building, and Bilbao is less than 300,000 people city, but for Spain quite rich. So after Madrid and Barcelona, this is the 3rd hotspot for culture and also science. And you need to know that I'm in a Basque country, so there's even a different language here. It's the oldest language in Europe, and have no connection to Latin languages, so they're also quite proud on this tradition, and they can be. But moving now to science, I'm working, as Sasha said, in the Basque Center for Materials. This is a center that have the luxury to not be connected to the university. And the idea here from the Basque government, or in Spain in general, is that they realized that, you know, everyone fighting for being the best in the world, and the Spain has not so much money like US or German or China. So they understand that they will not push the university very high, but what they can do is make centers that are quite comparable cheap to the universities, and at these center excellent science happening, because we're giving researcher the freedom to just do science. And we have 3 different science, so fundamental science, that is my center, technology science, and applied science. Yeah, and this is a quite comfortable position for researcher like for me, and I really like it, that you can really focus on science and have not too much the normal university bureaucratic stuff, and that's really swallow, I would say, at least half of your time. Then, why materials? So materials, why materials are important? You maybe realized, you have, when you study history in school, that you have certain like Stone Age, Bronze Age, Iron Age, that certain ages of history for humankind is named after the material, because development in humankind is connected to material. So material development is a key that we proceed as humankind. And we are now in the silicon age. Now it's nano, bio, multifunctionalized, and the material design age will now come. And this is more and more important, because every discovery is based on new materials a lot. And I just want to keep, because we learn in when I studied, so we have organic, inorganic, analytic chemistry, physical chemistry, but I would say this is why I choose also this 3 lecture. I would give you some ideas of material chemistry that basically combine everything, but in a certain way. And this is important to know. And also another important thing is to know this development spiral that we are. We had the scientific and industrial age. We are now in the information age, and we are actually quite out there. So information age is that we have access to all information, and we can do it. And now we're starting this symbiotic age to be combined with artificial intelligence. So, for example, if you don't know how to program it, it's nowadays no problem. You have artificial intelligence where you can tell them to program it, or you have artificial intelligence how to make images. So you tell the computer what picture you want. You really tell this in words, and then he creates one images for like this. You can make cover arts, for example. So then will come in the autonomic age, where we don't have to do anything, and then this one is where the development of technology will go crazy, because I think then we have really artificial intelligence that develop by themselves. So this is just interesting to know, and everything, as I said, is based on materials. And the idea is that we as a researcher generate new knowledge of materials that can be applied. So material science is always quite applied. So you apply materials for different purpose. Although I have to say, I don't like it so much, this applied thinking. I like more fundamental thinking, that you make fundamental some new stuff, and then after you have done this, you think about the application. But I don't think this is very good for creativity to think, okay, I want to solve this and then now try to solve it. It's one approach that is good, but I think at university level, at research level, we should more think, let's do some new materials with new properties, and then we will see how we are applying this. But okay, this is enough for the introduction, and I would come now for the lecture. So I like to speak about heterogeneous catalysis and how to study them with infrared spectroscopy. And I would like that we develop a way of thinking like detectives. I would like that we chemists, we're thinking like detectives, like Sherlock Holmes. I like a lot Sherlock Holmes, and thinking about the clues that we have, and then make a picture of this. And always, I would like that we change our way of thinking in one time very deep. So we will go on the molecular scale, and then we try to zoom out, see the big picture, and then try to make a story out of this. And the plan for today is that I will just give you today short introduction about heterogeneous catalysis. So what they are, why they're important, just very quick. Then a quick introduction about infrared spectroscopy. This is a technique very known, and it's nothing actually exciting about this. But then I would like to tell you how you can use this technique in a more advanced way with in situ infrared spectroscopy, and then about operando and infrared spectroscopy, which is really up to date. Yeah, so we go with a very old technique and then see how researchers took this to try to understand more and more things about the material, and at the end we want to have structure-activity relationship. Yeah, we would like to understand the structure of a material and then understand the activity and correlate both together. And if we do this, we can design better the material. And this is actually quite difficult, but quite interesting. And this is actually what you have to do as a chemist. So, importance of heterogeneous catalysis. First, materials, everything what you see around you or what you even wear are materials, and we need to produce them. So people forget sometimes, if you're thinking about this huge industry like Apple, Google, Amazon, but the biggest chemist company of the world is BASF in Germany, are bigger than all these three companies together, also from people. And they're producing also a lot of money. And of course, we have to produce all these materials. And in order to produce these materials in a very cheap and efficient way, you need heterogeneous catalysis. It's very important. So 90% of the production, they try to make it heterogeneous catalysis and they try to improve it. So it's a key technology in our society to develop new materials that can produce other materials that we need in our daily life. Or the other point is that the waste production, you know, that we are a society producing more and more waste. I think later in history, they will tell that they're just producing waste, and we need to develop materials, heterogeneous catalysis, that can use this waste as a starting materials to make this materials anew. And at the end, it's the best to have a cycle, you know, that you have something, use something, then it's waste, but then you change it again and you bring it again in a useful form. So this is very important. And just basically what heterogeneous catalysis is doing, it's about kinetics. So you have two big fields in physical chemistry, thermodynamics and kinetics. And this is the box, please, that you open. It's about kinetics. So about the rate direction, how fast are things going? It's just how fast things going. And you notice already that if you have a reaction, you have an activation barrier normally, and you need to pass it, and the catalyst help you to pass this activation barrier in order to have more efficient product that you want. So that's all, but this is very powerful. And one important example is the Haber-Bosch synthesis. You have nitrogen, you know, have triple bonds, so it's a very stable molecule, and you combine it with hydrogen and you form ammonia, and this is a molecule where you can make again reaction. So you form something that is can do not nothing, and then you bring it. It's a basic chemical that we need in order to produce other chemicals, and this is very important. And now I want really that you put in your mindset is that you have such kind of reaction. You have a heterogeneous catalysis, but what has happened is not this. You have many reactions. Behind this normal reaction are many different steps at the heterogeneous catalysis that are each one you need to understand in order to optimize the reaction. And this is very challenging. So, for example, Ertel, this was Gerhard Ertel in Berlin. He won the Nobel Prize for understanding this. So, in the Haber-Bosch Verfahren was 3 Nobel Prize winners. First, that you did it. Then, second, then also somebody discovered this, and then you had the production was a Nobel Prize, and then the understanding what happens at the heterogeneous catalysis. And this took them 20-30 years at the Max Planck Center, where you have a lot of money and just the whole institute just make research to understand this. And I just want that you understand how difficult it is, yeah, to understand one reaction with one catalyst, and this is very challenging. And here was done because the reaction is so important. But we need to improve this. And actually, what we want is, so chemistry, we have a molecular thinking in our head. So I like to think how atoms are arranged, especially when you do organic chemistry. But heterogeneous catalysis, we are at the macro scale. And at the macro scale, for example, what we can measure activity, selectivity, stability. And what we would like to do, we would like to combine correlate this to the molecular world, to the active site, intermediate, reaction mechanism. So we have, again, we would like to be detectives. Who did it? Where was he or she? Or how was it done? These are questions that we would like to answer in order to understand what happens at the heterogeneous catalysis surface. So please always zoom out, try to understand some very easy questions, yeah, big picture. So one time we zoom in and one time zoom out, and these are the big questions that we would like to answer. And we want to reach fundamental understanding, we want to have structure, activity, selectivity relationships. So we would like to correlate macroscopic finding with a molecular understanding. And what we have here is we make a reaction with input and we have macroscopic information. This we have. And what we need is we need a probe that interact with our black box, because we have a black box now, because we don't know what happens there. We see just things go inside, come outside, we don't know. We would like to have a probe, and then we would have molecular information. So we would like to understand what happens at the atomic molecular length scale in order to switch light in this box. So we would like to switch light. So this is the thing what chemists needs to do. We want to understand what happens there in this black box. And the question now is, okay, this is a nice idea, but what probe we need to use? How does the probe interact with the sample? And there is at first electromagnetic radiation. So what we have here, so we have electromagnetic radiation. It's just depending, the energy depending on the wavelengths of the frequency at the end. And here's the Planck constant. Just what is a Planck constant? Again, big picture. Planck constant is basically the slowest amount of energy that you can transport from something. Yeah, there is not lower energy, because then it starts quantum mechanics. So this is the lowest possible energy that you can have, that you can create, and this is then multiplied with the frequency, just for understanding. And then, very important, so we have the different electromagnetic variations there, depending on the wavelengths and then on the energy. So they have different energy. And then we have two important fields: microscopy, spectroscopy. Spectroscopy I will explain, and microscopy is just to see. So so things that we cannot see with our naked eyes, we need other we need other probes to make understanding, for example, the crystal structure of materials. So these are all probes that are connected to electromagnetic radiation. Such a thing is very important to just understand. We have just these probes, and then we can use this to make different images or different measurements. And another important box is that we need to understand, if we have a material, we have always bulk. So we have the bulk, we have the crystal structure, we can measure, we have a lot of instruments, various surface. So we have a surface. And this is very important. And you need to distinguish always a technique. When you measure, you need to ask, do I measure the bulk? Do I measure the surface? Or do I measure both? And another important thing is what Mr. Pauli said: God made the bulk, the surface was invented by the devil. And what he means by this is that you can measure very good the bulk, but it's very hard to measure the surface, and the surface change. And surface is really a different kind of a science and rules. And this is quite problematic. And it's really a pain to understand it. But the problem is, or the thing is, catalysis happened at the surface. Yeah. So and you understand now why these kinds of things are quite challenging, because you have something that we can measure, the bulk that will not change, and the surface is very dynamic. And just here a diamond, you know, a diamond is just carbon, but at the surface is hydrogen, for example. Yes, just at the external surface, that is basically the surface is defined as a defect between two phases. So it's hydrogen. You see, it's very different than what the bulk is. So you have a material that you have, as a chemist, a good understanding, but when you start to understand the surface chemistry, can be very different. But this we have to do. If we want to develop new catalysts, we need to understand the surface and what's going on the surface. And the biggest advice at first that I can do in general is think before you start a measurement. So if you're doing analytic chemistry or if you study a material, doesn't matter what you do, think before you do. So think, okay, what I have here, what is the method that I'm using, for what I'm using. Yeah, this is very, very important, because sometimes, you know, you study, then people say, okay, you characterize like this, and then you're starting to be like a robot, a machine, and without critical thinking. So always, I strongly recommend think before you're doing a measurement, and also, and during doing it, because we have eyes, we can always observe, think what you're seeing there. Yeah, this is very important. It sounds sometimes so banal when I'm telling this, but it's really a strong advice. Also, when you're working in the lab, you know, and a reaction happens, always look what you're doing and conclude what you're seeing. Yeah, this is very, very important advice. About spectroscopy, we want to speak about ER spectroscopy short. So spectroscopy is you have incoming light inside, and then you can have adsorption, you can have just reflection of light, also interact with matter. Let's hear it's matter. Then you can have photoluminescence, transmission, scattering. These are just different effects that happens if you have a light beam interacting with matter. Then important is for ER interaction of light, you have the Lambert-Beer law. Lambert-Beer law connects the concentration. You also have here samples, liquid, and the length of the sample and the concentration with the extension coefficient of something. And extension coefficient, I will come later to it. This is basically telling you how light interact with your matter, or later with a functional group, which is very important. And ER is about vibration. You saw this already in the picture. And vibration is I like vibration because you can easily imagine it. You know, you think just two balls connected with a spring. And, you know, here in the equilibrium state, nothing happens. But if you now make something, if you stretch it or compress it, you will find vibration. Yeah, they will vibrate. And this vibration depends how strong is the strength and the mass of these two balls. And this is depending. And then you can calculate this. This is I like this model because you can easily imagine it. It's certainly, if some people from theory here, they would say, oh, this is not true. But I would like to keep you, because you have quantum models. Quantum models is that each vibration have a quantum state, because even at 0.0 you have a vibration. So even if you have no energy, there's a vibration. And why it's like this? Because if there would be not vibration, you know, Heisenberg said you cannot relocate the electrons. And if there would be no vibration, you would directly see the place. And this is not possible in quantum theory. But I want just for you also to keep in mind that there is no right or wrong about models. So each model is an assumption, a description of something, and quantum theory, it's more accurate so far, but you need also to always ask yourself, does this model help me? And for IR spectroscopy, it's very clear that this model is very perfect for you. You can imagine this and can easily understand certain things that you observed at the macro scale and connect it to the molecular scale. So always take models, also two things. So there's no model right or wrong. It's just if it's helping you, this is the second important thing, helping you to understand certain things that you see as a chemist. And with this, you can concrete something. So this vibration model is very helpful. So imagination. If I would be now in Kiev, I could now make a bit gymnastic. We have stretching. You have two kinds of vibration mode. One is stretching. So symmetric stretching is, imagine here carbon, this is my head, and the hydrogen the hands. And symmetric stretching is when like this happen, or asymmetric is when like this. So you can make really nice gymnastic showing this. So this is bond length changing, and then you have angle changing. So if you have an angle here, you can change the angle. And these vibration mode, we have stretching and bending vibrations. So here we changing the bond length, and here the angle length. And then we have different kind of IRs depending on the energy of the incoming light. So we have near, short, middle IR. This is what we will use to interact with matter. And every time also important, this is a bit the same with computer nowadays, it's a bit difficult, but it's always good if you measure something and if you just know how its things are constructed at the basic level. And for IRs, it's important, for example, here you have the IR source, you have iris aperture, that's just telling you, you can open or close this like a window, so you can make it a bit more dark or a bit more light incoming. Then here's the inframeter and the beam splitter. I will tell you in a moment what is the beam splitter. Here's electronics, then the go beam here. And here are the detectors. These are two different detectors. Will not speak about this, but they just have different physical principles, how they measure things, and they are more accurate or not accurate. So, but such basic knowledge is always good to know when you're using the instrument, because what you see is just this here, and here you put your palette there. And then you taking just data, you have the interferogram, then you have a single beam, and then you have a spectrum. A spectrum, you take always a background, and then you substitute the background from the actual sample, and then you have your measurement. And beam splitter, as I said, is very important, because you don't want to measure every wavelength. There's the possibility that you put all wavelengths inside in the beam, and this can happen with the beam splitter, where you have a fixed mirror, and then a mirror that can change the position very precisely. And with this, you changing the wavelengths, you substitute them, you're changing a bit the position, and with this you're creating one big wavelength where you have basically every wavelength inside. And then you do Fourier transformation, where it's a purely mathematical approach, where you can deconvolute all the different wavelengths again and separate it. And with this you have the frequency and the different spectra. So very easy, you can now measure of a sample different wavelengths and see what vibration happens, and you can measure this. And there are 4 different important regions. One is the single bond region, the fingerprint region of different functional groups. This is very important. Then you have double bonds, triple bonds, and you have H bonding. So you can measure of a sample these region very easy. IR is very quick and very cheap. So, and this is I'm sure you have maybe already done this. And then you have different functional groups of a sample that you can easily measure. And what you measure is now some functional groups, and this is interesting, because functional groups you would like to have and to understand it from the heterogeneous catalyst, but I come later to this. Then again, to the models, don't think you have 2 balls that are heavy, they're connected with a spring, and then the vibration, how they are depending from bond strength and the mass. So, and if you're changing the bond strength, for example, double bond, triple bond, it's stronger, so the vibration would change. This is here shown. For example, so you have a stronger bond, 1 double triple bond, the strength, the energy, bond energy is increasing, and then if you have increasing in the frequency. And the same things with heavier things. So you have a heavier atom, and you have a decreasing of frequency. So just imagine you have 1 atom is the same, and then you make it heavier and heavier on the other side of the atom, and sure, the frequency is slower down because it's heavy, so this is physics and easily to imagine, and you can use this kind of physics. So this is very important here to use hydrogen and deuterium, especially, that you can study more the surface and understand, because you can easily substitute hydrogen with deuterium, and then you can understand a lot of things. So I would say until now, so just a basic introduction about IR spectra and how this is used. Maybe you already know about this, but the problem is, when I had this in myself in studies, so we had even several lectures about IR spectrum, but you have this already, and then you think, yeah, it's very nice, but IR spectra is quite old. And I feel more like this, we have also in Germany, I was in Berlin studying, so I was there where in the Schrödinger Zentrum, where Emil Fischer did synthesis, a very famous guy in Berlin, was a scientist, and we were also in these labs where even Emil Fischer was there, and it's look all very old, but when you sometimes look in the TV, you see such things. Yeah, and for me, was always wondering, what are up to now? Yeah, what is modern now? So I showed you now in techniques, this is quite old, and now we want to go to the step to show what is now up to date. How researcher using this technique to understand certain things, and there we are back to our detectives. So we saw already that ER spectra is very sensitive to different bonds, to different vibration modes. And the question is how we can use these vibration modes to understand our material, our heterogeneous catalysis. And there's one important technique, it's called in situ infrared spectroscopy. In situ means under vacuum. So you put your material under a condition that you control, and then you take pop molecules. I will tell you in a moment what are these pop molecules, to study acidity, basicity, or redox properties of the catalyst. So in situ can measure qualitative and quantitative. So you can also measure how much you have from certain things. If you know the extension coefficient, because we have the Lambert-Beer law, it's a very basic principle, but I want to show you how powerful these basic principles are. And then you can have a defined statistic condition, and then you can measure acidity, basicity with pop molecules. And the idea with these pop molecules, look, for example, CO, we will have this in a moment, they vibrate. And if they're interacting with your catalyst, they will change the vibration. And this change you use to understand it. So this is basically your magnificent glass, your probe. Sherlock Holmes had this magnificent glass, try to understand. And for us, it's IR, this. And what you have is in setup. I just want short to describe you how it's look like, that you can really imagine this. So here you have your sample, your pressed pellet. This is a closed setup. And then you have here a small volume, and it's very important. You know exactly, this is the dosing unit. You know exactly the volume of this dosing unit. And so you know then exactly how much you add to this. So these are closed waves. And then you have a joint, and then you have two pumps, the oil and the turbo pump. So at first you have always the oil, then turbo plant in order to clean the surface. And then you have here IR. You can here measure IR. And the idea is that you can probe you absorb something in the very known value to your sample. And you would like to measure acidity, for example. Acidity is very important. And you have Lewis and Bronsted acidity. So Lewis acidity, things that want like to have the electron or proton, it's a proton. Bronsted acidity is proton donor acidity. And you just want to measure it. You want to measure it, and you want to know how much it's on this and how you're doing it. So I told you already with CO. CO is a very nice pop molecule, and the HOMO, the highest occupied molecular orbital of a CO, is a slightly antibonding orbital. Meaning, it's slightly antibonding, meaning if you remove electron density from this pop molecule, you strengthen the bond. And when strengthen the bond, you will see a blue shift in the IR spectrum. And with this, we can monitor, and we know exactly that Bronsted acidity is much weaker than Lewis acidity. And you have, these are the typical vibration modes then, where CO in the Bronsted acidity, and here CO is at for Lewis acidity. And what I did, so sorry when I say I, but this is really what I did. This was during end of my PhD, magnesium fluoride. So my PhD, I did porous magnesium fluoride. And I tried to understand now the Lewis acidity of the sample. So there was no Bronsted acidity. And what you do always is you put small amounts of CO. So you put small amount on, then you see this, and then you're developing, put more and more CO, and then you see how the bands are shifting. And one important thing is when you add the first CO, always CO goes at the strongest Lewis acid. It's clear. And the strongest Lewis acid was here undercoordinated magnesium fluoride, just had 3 fluorides on it. And you have 1 CO, but also 2 CO molecules can go on this and then vibrate on this. So these vibration. Then we had 4-foot undercoordinated magnesium, and then we had 5-foot undercoordinated magnesium. So like this, you can study the different species, Lewis acidity species on the material. And if you could deconvolute here the surface under these peaks. So you have the surface area, and you would have the extinction coefficient. You could even calculate the amount, but you see that they are too much together. You can make assumptions, but they're not very accurate. But the next step is, so we have now in situ, so we can under inert condition can study the sample qualitatively and quantitatively. And then next step of in situ ER spectroscopy is to do it under flow, yeah, to have in flow in order to have more dynamic insight and study quantitative and qualitative dynamic properties of the catalyst. And here's the same setup that I showed you before, but you just have gas flow on this. So here's the sample, and you can have gas flow and can activate or play with the sample. And I will tell you in a moment for what we did. So what I did is we wanted to understand the adsorption of material for propane and propane. So it's very important to separate these samples. And what we did is we had activation stream under flow at different temperature and different times. And what we see that the separation efficiency start to increase drastically with the activation temperature. So this is an effect, and this you see. So you can study now, it's not catalysis, but separation, just as an example. And then what you see also is very nice is these IR spectra. You see certain species. Here, this is very sharp. And if you plot, if you take the area and the species, then you know also you see the development, how things, different bands are changing. And if you understand these bands, you can understand what happens at the surface of a material. And this is exactly what I wanted to show you now. So we have a material with 2 undercoordinated sites, iron 2 plus and iron 3 plus. This we know already from normal in situ characterization. We characterize, we know the bands, and now we're doing the flow. And we study when we put CO, we have 2 undercoordinated sites, so iron 2 and iron 3 plus. So we see the species, we understand, then we remove CO just by argon stream. Then we put NO on it. There we have different species. And when we put again argon over this, we see that iron 2 plus, the NO stays under this condition. And now we start staying there on this condition. And so iron 2 plus is now trapped or poisoning, is poisoned by NO. So we have only iron 3 plus. And when we put CO, now we can measure it now specifically CO on iron 3 plus. And then if we do activation, also we put high vacuum temperature at 250 degrees, then we're removing this. And this is, this is now a bit playing with the sample. I like this a lot, but you understand how your system reacts to shortened probes that you're giving, and you can use this. And for what we have here is that we can specifically poison iron 2+ with a species. And what we did is then we did the same separation when we had iron 2 and iron 3+3, and now we poisoning iron 2+, and then we do the separation, and we can say, oh, iron 2+ is the main species for this separation. And if we know this, then we say, oh, guys, we need to have a material with more iron 2+, because then the separation efficiency will increase. So you understand, and then you can react the material chemist. So this is just an example how you can really understand easily the sample and then improving something for separation effect. But going back now to the catalyst, here's a very important slide. It's how material characterization happens normally from a catalyst. What we do is, imagine you have a catalyst with IR. So we have freshly prepared catalyst here. Then what we're doing is we calcinating it. We activate it. You have always an activation, and then we do the reaction, and then we the catalyst is dead. And we can with IR measure each of these stadiums. So we can measure it. We can measure it here, 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 and here. But my question is, what is the problem with this? So, and what I find interesting, you know, always in science is if you know the solution of something, it's so obvious. But I can tell you that researcher did long time research about these different things, and they yeah, and then at certain point there was one young researcher, you know, come with fresh mind and say, oh, guys, we don't study exactly the most important thing. So what happens here? This is our black box. What happens here? So at the end, there was a famous catalytic person, heterocatalytic person, and they say, okay, what actually scientists is doing, we study the human life before a person is born, this is this state, and after he's dead. But if you would do this, you understand that you nothing understand from the catalyst, from the actually human being, you know, you don't understand actually nothing maybe, because what happens here can be very different what is before and after. So and I find this really fascinating because researchers needed really long time to understand this, that for heterogeneous catalysts that we study things before and after, but this maybe it's totally uninteresting, and we have no chance to understand the catalyst with this. And this is something very important also for maybe for you when you're doing science. It's very important, you know, you have a very specific topic, but it's always very good to, as for molecular and macro scale, we zoom very deep inside and understand very deeply, but it's sometimes good to go outside and see the big picture. You know, and you need to discuss both nowadays. So it's very important that you understand things at the bigger picture and then very deep in the specifics. So this is very important. And here, yes, I really like this example that, yeah, we study catalysts actually before and after, but as an example for human life, if you study human life before it's born and after its death, you will not understand nothing. It's not so drastic in this case, but it's just very important that you have this mindset to understand this. And again, we want to be Sherlock Holmes. We would like to understand, and after people understand this, that you say, okay, the catalyst I don't understand when I'm not observing it. So I want to observe the human life during its living. So what you need to do is you need to study a catalyst during its working, doing his catalysis. And this is where operando experiment is coming into play. Operando experiments study a catalyst during the reaction. So during its working, during its alive, this is the very important thing. This is the whole idea. And I want also to show you by this that once you understand it at the bigger picture, sometimes the idea when you're thinking, it's 50% of research, yeah, because nowadays researcher here sometimes we have a lot of instruments and people come in the lab and they just doing quick something and doing some experiment. But you know, people all over the world have many hands, but the key strengths that I always recommend is to use the mind, the head, think before you're doing something. And once you can do this, you know, the experiments can be 1-2 weeks and you can have amazing results. So really think before you're doing something. And Operando was this after researchers understand these things, they developed this. And what they did is they developed, I will show this in more detail now, a cell where you can carry out a reaction. So you have different flow steps, you activate, and then you make the catalytic reaction. Easier certainly gas reaction, because liquid is hard to measure, but it's also possible. And then you have then you know what's coming inside, and then you measure what is going outside with different characterization techniques. And this is what I mean. You have different probes and you can play Sherlock Holmes. So just here's in detail. So you have the flow. So here's the pellet, and here is the glass. So here's the IR beam, and then here's happened the catalytic reaction. You see, you have the IR from the surface. You can measure the IR, what's happened. You know from the gas, and then afterwards it's out. You can have again study with the IR, or you have mass spectrometer, chemoluminescence. If you have some chemoluminescence, and you have now a lot of data. So you will really understand at the molecular level certain things. What is what gas, how much you put inside. You know how much coming out. So again, you have a lot of understanding. So this is where we go really deep inside. But now I would like to again zoom out. What zoom out? When you do operando, what you need to understand from a catalyst. First, this. You need to understand that most of the people just watch. They don't do nothing. And you have then a reaction intermediate and active sites, which you want to know. And this active sites, you have also some poisoning species that's hindering about this. There's different ideas how to do this. So such things, it looks hopefully a bit funny, but such big picture things is very important that you have this in head, that you understand your details of the molecular things at the connected with this bigger picture. So you have this kind. You have this kind of game. You have people that just watching, that do nothing. You have just a few things that doing the work, and then you have people that maybe a lot of people that try to hinder to doing the work. And then also very important, you have different deactivation paths in heterogeneous catalysis. You have inactive sites. The active sites can just age over time, or you have other external constraints that hindering the catalytic sites to be happened. And you need to understand this. So once you have understand this, now we want to go hunting. So what is the first advice to hunt species? First advice is you need to distinguish between spectacular species. So species that don't do nothing. And believe me, there's a lot there. The problem is that when you have then later in IR spectrums, you have a lot of bands, but only a few really matter, and you need to distinguish them. You need to understand which species doing the work and which species just watch and do nothing. And then I hope you know the film Catch Me If You Can. It's a very nice film, and I like it a lot. And this is actually now the case, you know. You have Tom Hanks and Leonardo DiCaprio, and you want to catch Leonardo DiCaprio, but you know he's doing like this. He's very quick, and they are not easily to catch. So the problem is that species that you would like to understand, they are very quick, they are very fast, and easily not easily to hunt them down. And what is the second hunting advice? Be quick. You need to be very, very quick. You need to have a probe that is quicker than your species. It's very important. Yeah, like Lucky Luke. I don't know if you know, but I like Lucky Luke. So he was quicker even than his shadow. So like this, you need to be very quick to understand the species that have a short lifetime. And we're speaking really about very short lifetimes. But you need to understand it again. And once you understand this, you can react on this. So let's we have now seen the Borando spectroscopy. So there we doing the catalytic reactions and directly study our sample. And now IR, a very boring technique, but what IR can do this, just compare what can be observed with IR, and then we have reaction steps in heterogeneous catalysis. What different reaction steps we have in catalysis? Well, first of all, we have reactants that are transferred towards the catalytic surface. So, reactants just coming and going to the catalytic surface. And we can, with IR, we can see gas phase and diffusion phenomena. So we can see what does the gas phase looks like. If we know the extension coefficient, we can calculate how much we have, and we can see diffusion phenomena. So then what happens is we have reactant adsorption. So we have physi-adsorption, we have chemisorption or adsorption, and with all this physi-adsorption, you see, the frequency of your molecules of the reactants, they will change. And you see this with IR, and you can study them. You can understand if you know how a physi-adsorption species look like at your material or chemisorption, adsorption, you can understand this. So you will understand this just by the reactants adsorption. So what is the next step? Yes, surface reactions. Yes, we have this intermediate species, we have spectral species, we have surface state. And if we know this, we can study, we see this with IR. Yeah, again, we have a molecular understanding what's happened during the reaction. What is the next reaction step? We have product desorption. So again, physisorption, chemisorption, we have desorption of the product. And again, if we know from the product how the physisorption of the product looks like, chemisorption, how the bands are, we will see this. And we can even quantify this with IR. And then last but not least, we have the product transfer. So we have macroscopic, what we have at the end. So we have diffusion, and then we have the gas phase, and we know then exactly, okay, how much of the product we have now been able to now my English, able to produce is the word that I'm looking in my head. So produce. So we know exactly how much product we can have produced. And now really, please just digest this slide. You see, really, look, we have in the beginning, we can all things, all different here, reactants desorption, we can surface reaction, product desorption, product transfer out of the surfaces, what the different status that we can study with IR. And then you just see a very simple technique, I would say boring technique, but how powerful it can be if you using it and understanding during the using. Yeah, so powerful the things can be. And then what I told you already is the connection of the data. So you have now a lot of data, and here you have the IR, you have the in situ cell, you can calculate the mechanism, and then you can measure species with the IR, and you have even other analyzer, and you can understand and can make the puzzle. So what you're doing now normally with IR is you have all things understand, and then you try to puzzle this mechanism throughout, and you study this mechanism, then you have a theory, and then you prove this theory, then you play with the system. For example, you can, if you have an heterogeneous catalysis, you're changing something, you say, oh, this species is very important, and then when this species is important, you can just, as I showed you once, you can poison it or you can change it, and then you see how your system reacts on this, and with this you can proving the species formation. And this is quite powerful and quite nice. So I can really recommend you this kinds of science, and it's very, very important to how to understand the surface. But this is just the first step. Yeah, so this is just the first step. So you have the operando, you can understand the surface, but then you need theory. You need to play with kinetics. You need to understand the catalyst design and the reactor design. So this is engineering task. So what I want to tell you here, so this is that catalysis is really a multidisciplinary field. We need basically every researcher that is able, and I will show you this in the next slide, that you really can improve the catalyst and the catalytic performance. You need all these different kinds, and what you just show you today is one technique, and I try to show you how you take this boring technique and how you, with understanding the technique and your catalyst and the different steps that happened at the catalyst, how you can analyze this with one technique. And the important thing is, as I told you, to zoom in and to zoom out. So I try to also to inspire you to think in two ways. One thing is to think very deep at the molecular scale, and then to zoom out at the macro scale or the big picture things. And this switching is very important, that you improve your understanding of the system. And for catalysis, what I really like, it's important that you need even a third mode, so not only the molecular and the macroscopic mode, but you need at the end at each length scale. So catalysis happened at each length scale. So this was also a bit, researcher was very crazy about the active sites. The active sites, the species that happen, but catalysis happened at each length scales. So you have, for example, a porous catalyst where a reaction happened at the at the active sites, but then you have a porous support, you have catalyst pattern and the reactor, and at the end you have a macroscopic thing. So you have reactor chemistry. Reactor chemistry is engineering. So a sample needs to enter in the system. Then it needs to diffuse to the catalyst palette, to the porous support, and then it reaches the active sites at the molecular scale. Then the reaction needs to happen, and then again it needs to happen. Then the product needs to be dissolved from here to here to here, and then it's going out here. And this and this field, just to showing you what I showed you today with operando, is really more the understanding here. But you need also to understand your sample at the porous support. This is most of the time the non-active species, but they are important for the physics or the catalyst palette. So nowadays, 3D printing of catalysts that they have as optimized form. It's very important. You mass transfer, heat transfer. At the engineers are always crazy about heat transfer, because if the problem is also in the lab. If you make a catalyst reaction, you use milligrams, but here we speak about tons, and this is it's totally different kind of chemistry. So I want that you put this also in the white box, everything. And with this, I would like to give you some take-home message from today. One of the main take-home message is that heterogeneous catalyst is very important. It's a crucial field. So if you're interested in this kind of field, I hope you saw that you can enter from each. You can be organic chemist, analytic chemist, inorganic chemist. You can always enter in heterogeneous catalysis, because it's so important, because we would like to improve the synthesis of materials. It's one part, so to make them either to make them cheaper or better, or we want to use waste and make from this waste something useful. This is actually a growing area nowadays, to using waste, plastic, for example, to try to make out of them something useful. And for this, you need heterogeneous catalyst. Then I would like that you keep in mind that catalysis is complex. So you have a very simple reaction, but behind this reaction is really hidden a whole world. A whole world that happens at the heterogeneous catalyst at the surface. And what we want is to understand this world. We would like to monitor these different events at the heterogeneous catalysis and try to understand the reaction mechanism. Like what I showed you with the separation, it was easy. So iron 2 plus is active, and once we have understand this, we can improve this. This is very important, and I hope showed you that it's fun. So I showed you that with very old technique, infrared spectroscopy. I think it's quite impressive what you can do in this with this technique, just with one technique. And if you develop it, if you understand your system, how you can study this your heterogeneous catalysis. So I showed you that you have in situ and operando spectroscopy. Here, this is under vacuum, and then you have under reaction flow. And the idea is that you need both techniques to have property reactivity relationships. So what you're doing normally, if you try to understand a catalyst, always you put it in under conditions that you can control very good, and then you will start to test with prop molecules. You will measure the acidity, you will measure the basicity, you will understand the species, also the bands that you have in the IR spectrum. You study this, so this is some weeks of work. And once you have understand this, so this is if you have understand your playground, then you can play with it, and then you can make your catalytic reaction. So you study then the surface species, conversation, measurements, so what happens on this. And once you have done this, then you're going back because you will have questions, then you have bands maybe that you're not understanding, and then you try to understand this. And with all this together, you can make a mechanism out of this. And with this, I'm a bit early with this, I'm at the end of today's lecture about advanced characterization techniques, and I'm happy to answer any kind of questions.
Thank you, Stefan, for your nice lecture. I shall see. I don't see any questions in chat so far. Якщо не можете англійською задати, є питання, то можна, в принципі, українською, я тоді перекладу. От, якщо так, поки що не виникло. Okay, so I can ask a question then. You were showing on slide, I believe it was 39, I believe, or something like that. You were showing that you are assigning some IR bands to some specific Lewis acid sites. How do you do that? How do you know that this band, this coordination site is corresponds to this coordination state of magnesium? Is this something like general knowledge or?
No, this is not general knowledge. This is this is then a combination of other techniques where you understand this and theory like this. So for this porous magnesium fluoride, we assumed that we have these species from theory, and you can measure it also from fluid, solid state animal. You at the end, it's a connection from different techniques. So I told you today one technique you can understand a lot, but at the end, it's always coupling with other techniques. And again, you have a lot of data, make that in the picture. So what we know from other data is that we have 5, 4, and 3-fold underconnected magnesium fluorides in the sample, and then you're having this with CO, but you have also other probe molecules. And everything together makes then you come up with this kind of model that okay, these bands, things like this. So you cannot only measuring this, you understand nothing. It's really a connection of different techniques. IR different pop molecules and plus other techniques. There's no other way and no other chance to understand this.
Okay. So there is another question. And what are applications of these materials? For which reactions is magnesium fluoride used? So this is from our chat.
This was not so we have vitamin E synthesis. So there's a patent. I did this during my PhD, vitamin E synthesis, because vitamin E synthesis is nowadays homogeneous catalyst used, and this is not good. And we had very good results for vitamin E synthesis, but it was also interesting. I did a patent on this. And then you are young, you're naive, you don't know nothing. But the industry as vitamin is produced in very large scale, so the industry always planned 25 years. And if they have they had a production with homogeneous catalyst, and this homogeneous catalyst, and this catalyst was better. But they said us, it's very nice, your results, but we will not touch our production, because they have these big reactors and they're just done for this, and it doesn't matter if even something better and cheaper, but this is just from the lab scale. But to make it an engineering, to engineer really a production scale is a different purpose. So yeah, this is vitamin E synthesis was quite nice, but here was more important that you have high porosity, because normally fluorides don't have porosity. And my professor at this time, he developed a Sol-Gel process for fluorides. I was handling a lot with fluoride and HF in the lab, and to make porous fluorides. So he did also aluminium fluoride and other calcium fluoride, and was interesting for catalysis, or also he could press them for some glasses. So yeah, this was interesting. Yeah.
Thank you. And there is one more question. How the size of magnesium fluoride nanoparticles, were there nanoparticles in fact, or it was just porous magnesium fluoride?
Yeah, there was nano, but there was agglomerating. I never had. So you saw in the TEM that they're agglomerates, but I could never separate them.
Okay, so these were not nanoparticles. So
nanostructured materials, I would call them, but not nanoparticles.
Okay, I see. Thank you. And one more question: how expensive is this special equipment for in situ and operando IR spectroscopy? Is it much more expensive than usual? For example, IR spectrometers has it to be specially constructed, or something like that?
Yeah, so you need to buy an. Wait 1 second, where we are. Yes, also you have an IR spectrum, but sure, this in situ operators you need, as they are constructed. So this is, I think, I'm not sure if you can buy it, but so you have an engineering department, they need to construct this, yes, and you need to buy this. So you need to, so this is really engineering, which is actually very important, because nowadays, I miss in research this material characterization. Nowadays everybody makes a lot of materials, but to study them, this is very challenging, and you need institutes that really develop approaches how to study these materials. Yeah, but you need to buy this, but I would say it's still not so expensive when you compare to other techniques. So so because the binding, you need just to buy some things, the spectrum. If you buy an SEM or TEM, this is by far more expensive. And it's much more fun for me to, as I have used both, also this kinds of things to use, and it's really pleasure with these systems to play. Also I enjoyed it a lot.
Thank you. So I see that seems there are no other questions. So, okay, if there will be any questions that might appear later, for example, when someone will be watching us on YouTube, then you can ask this question on the next lecture, or perhaps in comments on YouTube, and I will ask them to Stefan and pass them to Stefan. But for today, I believe that we can finish our lecture. And thank you, Stefan, again for being with us today. And I hope to see you next time.
Sure. Yeah, thank you, Stefan. Thank you. Thank you very much.
You're welcome.
Thank you.
Bye.
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 Mm-hmm.